Welcome everybody to Tasking's new three-part webinar series. My name is Florian Süßmeier. I'm Product Marketing Manager at Tasking, and I will be the moderator of today's webinar. During our last webinar, part 2, our FAE introduced the main features of the Tasking performance optimization tools and showed you how you can improve the operating efficiency of your embedded AURIX safety application. In today's third and last part of the webinar series, our field application engineer Ahmed Barakat will guide you through the Tasking safety products. Ahmed will showcase the Tasking Safety Checker, a static analysis tool that can help you to guarantee freedom from interference of software modules. He also will be introducing the Tasking Compiler Qualification Kit, the functional safety work products that can help you certify your embedded AURIX application up to ASIL-D level. We are active partners with leading OEMs and tier ones, and our focus is safety critical software development on multi-core architectures. Tasking provides a complete development environment that allows software engineers to develop reliable, safe, and high-performance applications. We are active in regards to the software development V-cycle and provide tools that can be used in different stages. For software development, for example, we are offering the Tasking VX toolset, consisting of a compiler, linker, locator, and simulation debugger, developed according to ASPICE Level 2 and TÜV certified according to ISO 26262 up to ASIL Level D. In addition, with the latest qualification kit, Tasking is now also supporting IEC 61508 up to SIL 4 for industrial applications. Supplementary, Tasking is offering LAPAC performance libraries and qualified CMath libraries as per ISO 26262, the Tasking embedded profiler and the multi-core performance tool, which have been covered in the last webinar, support part of the integration testing. And in addition, we offer a static analysis tool, the Tasking Safety Checker, to ensure freedom from interference, which will be showcased in today's webinar. For hardware configuration, the Tasking Pin Mapper completes the portfolio. I want to inform you also that this webinar will be recorded and will be available later this week on our website on tasking.com. Then you can click on our resources menu and you will find the on-demand webinars. So all parts of this three-part webinar series will be online. Also, the shown material, the presentation, will be available for you to be downloaded. The link you can see here. It will be uploaded right after, or I think it is already uploaded, so you can directly go to this link and get the slides, which will be presented by Ahmed. Now let me introduce you our speaker today, Ahmed Barakat. He is TÜV certified functional safety engineer with computer engineering background. He focused on the embedded software in the automotive space and previously worked at Intel, IBM, Valeo Egypt, and then moved to Germany as a senior software engineer at Magneti Marelli. Later on, he moved to Wind River to support different OEMs building their autonomous driving platforms. And currently, Ahmed is working as a field application engineer at Tasking and supports a wide range of customers in Europe and Asia. He's interested in the multi-core development with focus on functional safety, security, and also the qualification aspects. If there are any questions during the webinar, please use the chat function or also the Q&A function of Zoom. After the presentation is finished, all of your questions, at least we will try to answer all of your questions after the session has ended. Now let me hand over to Ahmed.
Thank you, Florian. Is the sound quality good?
Yes.
Okay, so hello, everybody. Thank you for your time today to attend the third part of the webinar series. In the previous two webinars, we cover two different aspects. So the first aspect was a tool chain. And in this webinar, we saw different aspects of the tool chain itself associated as well with a bin mapper. So we saw in this webinar how we could generate C code in order to be used with the AURIX microcontroller. And at the same time, we saw how tasking compiler could cover the OEM software requirements like the AUTOSAR and the operating system selected by the OEM. We saw as well, additionally, interesting features that comes with the tasking compiler toolchain, including, for example, measured C checker and cert C checkers for security applications. In the second part of the series, we cover the optimization aspect and how could you optimize an AURIX-based application using different tools like embedded profiler and multi-core performance tool. We saw as well different benchmarking comparing tasking performance in comparison to the open source compilers. So in order to check all of these points, please refer to the previous two parts of the webinar series. Today, we are going to cover the safety aspect. And in order to illustrate or highlight the safety aspect of the toolchain, we are going to consider or build a safety use case around an EBS system or electric power steering system. So we are going to see the architectural overview and we are going to define the item itself. We are going to build the safety use case around it. And after that, we are going to share with you the different challenges that we face based on our experience with the safety use case for the EBS. So this is, as we already discussed, the agenda for today. We'll see the architecture and we'll dive directly into the challenges. And after that, if you have any questions, please write it down. And after the session, we are going to answer all of your questions. I would like to highlight first some light on the item definition. So our system today is the electric power steering. So this is how this looks like in the reality. And the architectural overview of the system looks like this. So in this architecture, we having the master microcontroller, the AURIX based microcontroller. And besides that, we have some driving circuits in order to drive at the end the motor. And because it's a closed loop control system, a feedback is needed. And this feedback is fed using the rotor position sensor, and it feeds back the rotor position to the microcontroller. Besides that, we are getting as well some inputs from the torque angle sensor. All of these components are replicated on the right side of the architecture in order to guarantee fail-safe mode or fail-safe operation. So you will find here another AURIX-based microcontroller, and in this case, it's a slave microcontroller and a slave driver in order to drive as well the motor. If you want to have a kind of overview about the application features, so these are the features we already used, and these are the system benefits as well, building such system using the AURIX microcontrollers. And Infineon provides some guidance as well about building different systems, and EBS is one of such systems, and they suggest a certain series or a certain families for the EBS, and such devices are the proposed devices from the Infineon point of view. I'm going to speak a bit more from the software perspective. So we already experienced it in the last webinar that the OEM requirement doesn't allow us to use the core number 3. So that means we are going to develop the EBS application on core number 0 and core number 1 only. And for the core number 0, we are going to use a certain components of the architecture. For example, I'm going to use as a general purpose timer, because this is basically the heartbeat of the system. And at the same time, I'm going to use the I2C interface as a communication protocol for the communication. On the core number 1, I'm going to use as well the general purpose timer and the communication peripheral I2C. And at the same time, I will initialize the general timer module or GTM module. And I'm going as well to use the analog to digital converter. So these are the components that I'm going to use. In order to use or build this EBS, I already use ILLD or Infineon low-level drivers. And Infineon low-level drivers provides the software in order to interact with all of these preferences. So I didn't write the drivers myself. I use the Infineon low-level drivers. I will give you here in this slide architectural overview from the software perspective. So what are the software components that are running on core number 0? And what are the software components that are running on core number 1? So on core number 0, as a best practice, I enable the interrupts at the beginning. And after that, I started the system timer. I highlighted or I make some lights on. And after that, I give a trigger to the core number 1 that the core number 0 is finished with its initialization. So that means the core number 1 can continue forward with its own initialization. And after I give this trigger, I continue initializing the I2C and the app timer manager. And at the end, what's happening basically on core number 0 is I am getting the debug information using the serial interface connected to the computer. So it's only providing here a certain sniffing on the debug information, not too much complex running on core number 0. But on core number 1, basically most of the work is happening. So again, at the beginning, I already enabled the interrupts. I get the notification from core number 0 that the initialization for core number 0 is done. And after that, I start the app timer and initialize different peripherals. Like we already saw, general timer module, capture and compare unit, analog to digital converter. And after that, I am managing here the state machines, the different state machines for the motor. So there is a master state machine in order to control the status of the motor. And there is another state machine called slave state machine that's triggered if there is a certain safety failure or if there is a certain failure happens inside the state machine driving the motor from the master state machine. So if there is a certain failure happened here, the slave state machine take over and drive the motor. Before jumping into the software, to give you an idea how the software environment look like, I would like to give you an in-picture of the product itself developed. So in this picture or video, you will find here I already use one device from the supported devices from Infineon, and I use a neutron control board in order to develop such system. Neutron control board has a motherboard, and on top of this motherboard, you will find here the AURIX device or the AURIX microcontroller on top of it. And you will find here a certain conditioning circuits and interfacing circuits driving the motor in this case. And you could consider here this interface as your driving wheel. So this will set the motor to a certain angle. So this is how it looks like. The motor is running. And I will simulate a certain failure in the hardware by clicking a certain button. So I will get an input from a button, And when I receive this input, that means there is some failure happened. That's why the motor stopped rotating, and the slave state machine is triggered and drives the motor again. I would like to share with you as well the software environment. So I will open here my software environment. I have tasking Eclipse IDE, and I use the latest compiler version. And this is the project that I already use for the system. And you'll find here there is already auto-generated startup codes for core number 0 and core number 1, and as well core number 2. We will not dive deep into such details. When all of the startup code already converge to a certain point where this is the main, so every single startup code, after it's finished, it converges to this main. And the main use some intrinsic function in order to get the core ID where the software is running. And based on the core ID, I'm executing certain parts of my application, either in core number 0 or core number 1 or core number 2. As you already see in the architectural view, I already enabled the interrupts, checking some LEDs, doing some stuff related to debugging as well. But most important here is I am just looping and getting all the information from the shell connected to the USB interface. If I go back here and if I go to the core number 1, this is the software that's running on the core number 1. And again, I enable the interrupts, do some initialize preferences. And after that, what I'm doing in this loop is I'm managing the core, the state machine, the master state machine, and the slave state machine of the motor. For every state machine, you will find a different states where the motor could end up with. So for example, at the beginning, it's in standby and then spinning and then BLDC on. So that means the motor is running. And once there's a certain failure appeared, so you will find the motor ended up with this BLDC failed. As I already mentioned, I already use Infineon low-level drivers. And in order to integrate the Infineon low-level drivers with my project, I create another project in order to maintain the scalability of my project. So I create here a reference project that reference to the Infineon low-level driver project. And under the Infineon low-level driver project, you will find here the different modules that are provided with the ILLD example. And what I did for this project is I already compiled this separately and compile it and put it as a library. So this is the library out of this project that contain all the software needed or compiled for the Infineon low-level driver. And when I'm using my application, I'm referencing to this library, and at the end, I'm going to link against this library as well. So this is a better approach if you have a complex project to divide it into smaller parts, and after that using project references. So in this case, you could have a very modular application. For my application as well, if you go to the properties, and then if you go to the settings, you will find here the C and C++ compiler. And you will find here, these are the compiler options that I'm using for my EBS application. And this is the assembler options. And this is here, the linker options. And the environment give you full flexibility and full control. How could you optimize your application? If you want to optimize it most, or you don't want to optimize it all, and the ranges in between. And at the same time, what is the direction where you want to optimize your application? If it's more in the speed direction or more on the memory size direction. So I hope by this point that the software environment and the architectural overview of the application is clear. I will go back to the presentation. And after showing, or after we already saw the architectural overview of the EBS, we are going to dive in the different challenges related to the EBS system use case. We are having two challenges here. The first challenge is, as I already show you in the example, I'm using a certain compiler options. And as a safety expert, I need at the end to qualify such compiler options. So this is the one challenge or one big problem that you could end up with if you are developing safety critical applications. How could you use, or how could you qualify the tool chain that you already use in order to build your EBS application, or in general, any safety critical application? The second problem is, as we already saw, there are two state machines, and you don't want to make any dependencies between these two state machines. So for example, you don't want, while running the master state machine and the master state machine is working very well and there is no failure happen, you don't really want, for example, a certain pointer that trigger the second state machine or the slave state machine in this case. And how could you fix such problem or approach such challenge? You could approach this by achieving a very basic principle related to the software development called freedom from interference. And the challenge is how I could achieve this freedom from interference between the different software components. And this will lead us to basically the second challenge that we are having here. We will cover first this challenge, related to the tool chain qualification. And after that, we are going to see the second challenge and what are the possibilities in order to fix this problem. For the first challenge related to the tool chain qualification, we already experienced that there is a certain compiler options, assembler options, and the linker options. All of these options together, it will be combined and it will make something called toolchain compiler option profile. And at the end, you have to qualify the profile that you used for your EBS application. In order to qualify these tool chains, you have to select a certain qualification method. The ISO 26262 standard offer two basic qualification methods. The first one is called validation of the software tool, and the second qualification method called evaluation of the tool development process. Based on the confidence level in the tool and the ASA requirement that you are having, you will end up with a certain qualification method. Theoretically speaking, the qualification method called validation of the software tool is used for higher ASIL-based applications like ASIL C and D. And the qualification method called evaluation of the tool development process is used for less ASIL-based applications like ASIL A and B. We are offering the tasking compiler qualification kit that could help you in order to provide the technical argumentation and the evidences covering these two qualification methods. Tasking compiler qualification kit consists of three parts: the safety manual, issues portal, and certain scripts. In the safety manual, we are describing how could you configure the tool chain for safety critical applications. For the issues portal, we are providing you with all the issues and mitigations for all the available issues. For the scripts and instructions, the customer could use such scripts if he ended up with a decision to qualify the tool chain in his organization. We don't, though, recommend this direction. Let's dive a bit deeper in our safety manual. For our safety manual, you will find the first part covering the overview and the environment setup for the testing of the compiler. The second part will cover the different qualification methods we already saw in the previous slides. And then the third part, it covers the malfunctions and mitigations, so the problems and mitigations for such problems. Sometimes there is more than one mitigation for one malfunction, because sometimes mitigation is not applicable in a certain use cases. That's why we could even provide more than one mitigation for one malfunction. Then we are giving in our safety manual some toolchain guidance, where we are describing our safety use case for any safety critical application. And at the end, we are providing here the qualification evidences, where you could wrap up in one or more work product and deliver it to the authorization entity, like for example, TÜV. You are eligible to order the safety manual teaser document. And the safety manual teaser document, it is the first part of the safety manual. It's around 10 to 12 pages. And using this teaser document, it gives you the impression what are the content of the safety manual, and you could decide if this is suitable for you or not before purchasing the qualification kit. Inside the safety manual as well, beside providing the qualified use case, so these are the compiler options qualified for, or this is basically what we are recommend for the control application, for the compiler, assembler, and the linker. These are the supplied options. And besides that, you will find inside our safety table, safety manual, a big table that lists all the compiler options. And besides that, you will find the status of any of these options, if it's qualified or not. And besides that, you will find as well our recommendation, if it's positive recommendation or neutral recommendation or a negative recommendation. For example, negative recommendations, that means we don't really recommend this compiler option for any safety critical applications. I would like to give you some overview about what kind of tests that we are running on our compiler. So we are running more than 125,000 tests with more than 60 test suites against our compiler toolchain. And at the same time, we use different option permutations. So that means you are eligible to use any combination of all of these options as long as it is qualified. And you don't need any extra work to qualify any permutation of any of these options. And by considering the permutation, definitely this number will jump and it will end up with 237,000 tests we are running on our tool chain. These tests are either standard test suites or self-developed test suites. As examples, we're using Perennial, for example, or Nullstone, or Plumhole, and so on. It's really, as you already see, a big list. Besides that, we are having as well our own tasking test suite that we are running as well on our compiler technology in order to test the compiler toolchain. How often we are running the tests? For the functional tests, we are executing it every night against the master branch. And for the coverage tests, we are executing every weekend on the master branch again. If there is a certain fix or a patch available, so that means we are doing a full regression for the tests executing for functional and for coverage tests as well. You will find here the compiler test suite examples, the description of the compiler test suite, how many test cases, and most importantly, you will find that the number of failed test cases are 0 for all the test suites that we already used, which gives you as well the confidence that tasking compiler is already designed, taking in mind the safety critical applications. I'm going to cover the second part of the qualification kit, which is the issues portal. This is how it looks like online. So you will find here the different compiler architectures that we are having. For example, I will select here the last version of the Tricore compiler, which is version 6.3 R1. If you click on this version, you will end up with something like this, and you will find all the open issues, the severity of the issue, which is software integrity level, the component where this issue exists, and a summary of the problem. If you click on any of these issues, you will find more details about the problem. For example, the status of the problem and the severity of the problem and description, and most importantly, the mitigation of this problem, how I could fix this problem. We encourage you to check the issues portal because you will most probably not be the first one experiencing such issues. So most of the issues already reported either by our engineering and testing team or even by our customers. And we are providing certain mitigations and certain fixes for such problems. That's why the probability that you have the solution available for your issue is very high. I would like as well to highlight the different technologies that already existed in the market related to the compiler technologies. So for GCC, which is the open source technology, you will find that as a number of the issues that exist according to the version of the compiler that you are using. And this is here the number of the bugs. And if we focus only on the gray color, which means the new issues or the new problems already introduced in the compiler, you will find the issues are already increased with the version up to version 4, and after that it declined a bit, and then it's kind of stable around 400 bugs. For the LLVM, you will find that the gray color is always increasing. So that means the number of bugs introduced in newer versions are already increasing, which gives you as well the impression that such technologies and such compilers will be kind of challenging when it comes to developing safety critical applications with such technologies. On the other side, if you see the tasking, we are having our own Viper technology. So this is a compiler patent technology that we are offering to our customer. And once we already have a new issue or a new defect, it will be reported and it will be fully controlled in our database. And I will give you specific numbers related to the severity of the bugs. So the severity of the bugs is reflected with the cell. So cell means the software integrity level, as mentioned, and it gives you a hint about how critical such issue is. It has a value of fear for cell 1, cell 2, cell 3, and cell 4. Cell 1 means it's very low critical. Cell 2, it means moderate critical. Cell 3, it's basically major criticality. And cell 4, it's kind of very high critical. So if you are developing safety critical applications, as an advice, please have a look on the compilers that has how many of cell 4 and cell 3 issues existed in the compiler that you are using. From our side, the cell 4 issues once already existed. It has always the highest priority because this reflects the criticality as well of the problem, and it takes on average 6 working days by us to fix such cell 4 issues. For cell 3 issues, which comes in terms in the rank number 2, in terms of priority, it takes on average 16 working days. Since we already applied the ASPICE process, we already noticed that it's only one cell 4 defect was not founded and uncovered in version 6.2 and later versions. You will find always all the issues already existed in our issues portal, and the issues portal is updated daily. I can emphasize how important it is when it comes to the cell 3 and cell 4 issues existed in the compiler. If you already decided for other open source technologies, please make the exercise of finding out how many cell 3 and cell 4 issues existed in the compiler of choice. That's why I give you here a kind of overview how many cell 4, cell 3, cell 2, and cell 1 issues existed in our compiler. You will find here, starting from 2015 till at the moment, so all the issues with the cell, all the cell fear issues already fixed in the previous 3 years. For 2020, we have only one cell 4 issues. And you could notice as well how beautiful the curve is going down. So that means even the number of the issues of the cell fear is already decreasing with the newer versions. For the cell 3 issues, all the previous issues till 2018 already fixed. In 2019, there is a 1 issue still open, and for 2020, there is 3 issues open. This is how it looks like for issues for the issues of the cell 2, and this is for the issues for the cell 4. The down in this curve, this is because we already applied as well the ASPICE process, and this gives you as well a better understanding, a better quality of our compiler. So this is the tasking assessment result. And you will find here different processes like project management, software design, quality assurance, and so on. And you will find here the evaluation, which is F. F means fully achieved, and the capability level in this case is 2. We already experienced that for safety critical applications up to ASIL D, you will most probably need the capability level up to 2. For example, capability level 3 is not needed for all of our customers. From the project point of view, I would like as well to highlight the breakdown of the tasks if you are using tasking compiler against if you are using open source compilers. For the tasking compiler, you will find the breakdown of the tasks. It's really very simple and very easy. So I will estimate here a 1 week of a team ramp up. So where the team will understand the requirements, will read the safety manual, will understand the safety manual, and so on. The second week here, it will be for creating the work product, and this will be the output of the qualification effort. And in this case, you need only to create one work product that's called software criteria report. And most of the time inside this work product, you will refer to the safety manual. This will drop the work needed for creating the work product dramatically. And then I will put a 1 week for the final documentation of the work product, and if there is a certain changes needed on the fly. So on average, if you are using the tasking compiler, the tasking qualification effort will be on average 15 man days approximately on the customer side. On the other side, if you are using the open source technologies, you will end up with lots of tasks to be done. You will first start with the ramp up as already started here. And after that, lots of exercises needs to be done. Like for example, tool chain classification, and define the tool impact, and there's tool error detection, and the tool confidence level, and decide on a certain qualification method. And after that, execute the different qualification methods. And then select the different compiler test suites and execute the compiler test suites. And let's assume there will be kind of problems when running the compiler test suites from the first run. And then the analysis is needed. And after that, a fix is needed. And after that, once everything run smooth, hopefully at the end, you will end up with the documentation part and creating the work products. And in this case, you will need two work products. The first work product is the same like here. It's called software criteria report. And the second work product is software tool qualification report, where you are going to document all the work that's happened inside these tasks. And then after that, a confirmation review is needed. And then finally, the final documentation. If you notice, you will find a really very big change in terms of time and in terms of the resources needed and the financial aspects as well if you decided for tasking against GCC compiler. And the conclusion out of this exercise is if you use the tasking compiler, the qualification effort will be approximately reduced by 80% compared to the open source compiler. In order to summarize everything together, if you use the tasking qualification kit, you will end up with less qualification effort because less work products are needed. And at the same time, the qualification kit could be used not only on the automotive space, but in other spaces like industrial applications as well. For one or another reason, customers could need more support. That's why we are offering as well a custom use case support for our customers, where we are going to provide more support to our customers in order to pass the qualification. We're going to cover the second challenge that we already experienced it with the electric power steering system. And the second challenge is about freedom from interference. As we already saw in the software, this is the state machine for the master state machine to drive the motor. And this is the slave state machine to drive the motor. And these two state machines, they should be independent from each other. And there will be only triggering for the second state machine once there is a certain problem happened with the first state machine. You don't want, for example, while the motor is running and everything is fine, that you don't want to trigger the second state machine. This will not be accepted because it will put the system in a very dangerous state. And at the same time, you need only the triggering of the second state machine just in case there is a failure of the master state machine. So the point here is to avoid cascaded failures. And in order to isolate the two state machines, the master state machine and the slave state machine, you will find different possibilities or the different solutions available in front of you. The code review. So you could do, or you could follow a code review process where one reviewer could review the developer work, but at the same time, the code review itself, or the effort that's needed by the code review, it's proportional to the code size. So if you have really a big chunk of code that needs to be reviewed, so that means the effort for the code review will be big. And at the same time, the code review, it really doesn't fit in your agile process. And at the same time, the quality as well of the code review, it's dependent on the reviewer that's going to do the work. On the other side, if you check, for example, the tasking safety checker, which is a static analysis tool that's ASIL aware, you could use this tasking safety checker in order to automate such code review process to achieve the freedom from interference. The tasking safety checker support the C language at the moment, and it provides you as well with a very precise positioning of the safety violations that happened based on the source code base that you are having. Not only that, you could use as well the safety checker to make measured C and third C checks on your code. And this is one of the possibilities as well offered by the tasking safety checker. Besides that, this safety checker, it fits in your agile process because, for example, you could use it with your Jenkins workflow. So if you are using any continuous integration platform, you could embed it with your workflow, and it should not be a problem at all, because tasking safety checker, it's a command line tool. So with just one line in your script, you could just call it and expect the report out of it. And then you need to check or have a look on this output or the work product out of the safety checker. How to use a safety checker in a safety critical application? So first step is define the safety levels. What are the safety levels that you are having? Do you have, for example, ASIL A and ASIL B software components only? Or do you have ASIL D software and QM code? Or do you have safe and non-safe only software levels? So you need to define here in this step the safety levels that you are having. And after that, you have to assign a safety level to the software component. So for example, one software component could have an ASIL A, and another software component could have an ASIL B, for example. And after that, as a third step, you have to define the access rights. And the access rights are the rights between the source and the destination software components. What are the rights between the software components? Can I only read from the different software component, or write from software component, or execute the other software component? And then the fourth step here is running the safety checker from the command line. So the safety checker check all your code base, and after that it will generate a work product where you will find all the violations existed in your source code. And the safety checker give you a precise positioning of your safety violations. So it highlighted you the file name and the line of code where such violation is happening. We're going to see it in the coming slides. So this is the configuration for the safety checker. This is how it looks like for the EBS application. So I have here different safety classes. So I have one ASIL D class here, another ASIL D class here, and then QM safety level, and I have another, for example, main safety level or whatsoever. Our focus here is only the ASIL D BLDC master and slave one, which is M2 in this case. Here I am defining the rights, the read and the write and the execute right between the source and the destination software component. And here I am assigning a certain ASIL level or a certain safety level to a certain software component. And here you could find a matrix overview about the rights between the source and the target components. Beside that, the safety checker will generate a list of all the files that already checked, and if it's used or not, and the associated safety class available. Let's have a look on the work product out of the safety checker. We have here the first part. It's called call graph. The safety checker generates for you a call graph for your whole application, which function called, which function called, which function, and so on. And the second part here is the access violations. And as I already mentioned, in the access violation part, the safety checker shows to you in which file and in which line of code this violation happens. Besides that, the safety checker could give you as well some coding guideline tips. For example, here it could highlight some coding guideline deficiencies, like if you have a possible infinite loop. So such coding guidelines will be detected and it will be done, it will be highlighted to you. That's all beside the safety configuration, which is a matrix overview between the source and the destination part. The takeaway for today's webinar is, in tasking, we are building a safety concept. And for our tasking safety concept, we have the compiler, and besides the compiler, we have the qualification kit. And this qualification kit provides evidences for ASIL D applications with tool confidence level 3. And besides that, we have as well the freedom from interference safety checker tool. Besides that, we have as well qualification libraries. So that means we are providing, or this is a kind of progressive work. So we are going to qualify the different compiler libraries that are shipped with the compiler itself. And besides that, we have as well the static code analysis tools where you could use the Measure C and Cert C checkers. The tasking VX toolset is already certified by TÜV Nord, and this gives you as well the confidence in the tool. And the tasking toolsets are already certified. So there is a really big difference between certified and certifiable. The competitions tool are certifiable, and certifiable means it could be certified, but at the moment this is not certified. So you have to check the tools that you are using, if it's certified or not. And if it's certified, it will be a big relief for you. Otherwise, you will end up with certain frustration and as well a big effort, because you have to do the work in order to qualify the tools that you are using. And this definitely as well has a direct impact on the project cost. With this slide, I'm done with today's webinar. I hope I gave you some insights about applying the safety concepts on the EBS application from the toolchain point of view, and at the same time achieving the freedom from interference principle using the safety checker. I will give back the control to Florian.
Thank you, Ahmed, for your presentation. And thank you, everybody, for joining this last part of our new webinar series. I would like to motivate you to ask questions now. Here is one thing. Let me ask here the question to you. To achieve the freedom from interference, beside read-write access rights, what measures are made by safety checker?
Okay, let me read it again. To achieve the freedom from interference beside read-write access rights, what measures are made by the safety checker? So for the safety checker, as I said, it's static analysis tool, and it controls the calls between the different functions. So if a function is going that has a certain ASIL level or safety level, call another function, the safety checker control if this allowed or not based on the configuration that you already give in the configuration file. And if this is not allowed, the violation will be highlighted in the outcome of the safety checker. Another point, for example, you could use the safety checker in order to check if there is a certain pointer try to access certain memories that's not allowed to be accessed or not. So this could be as well highlighted with the safety checker. And another measure in this case is, you could use the safety checker for the static analysis guidelines in general, like what we already saw in our webinar with this infinite loop. This is only one example, but we have a complete list of the issues that the safety checker could be detected. I encourage in this case to have a look on the product overview from the safety checker, and maybe it could be as well useful for the customer in this case to request a trial version for the safety checker in order to decide if this is helpful in this case or not.
Okay, thank you, Ahmed. Then there's another question from a user. I cannot get the benefit of the checker tool as the same configuration is applied to the MPU. Please clarify.
For the safety checker, it is not a replacement to the memory protection unit, but the point here is in which stage you are going find the safety violation? Do you like to find it during the development phase, or do you like to find it after the integration of different software components? For using the memory protection unit, it's required that you already combine everything together in terms of software components, compile it, flash it on the ECU, and after that, turn the memory protection unit on, after you configure it definitely, and put the system under stress in order to check the corner cases and hopefully get certain safety violations in this case based on the system stress that you are putting. But on the other side, from the safety checker point of view, it is a static analysis tool, so it could be applied as well on the unit testing and while you are developing different software components, and you could run it on the daily basis. And this is basically the difference or the differentiator between the safety checker and the memory protection unit. So the best scenario in this case is to use the safety checker in an early stage of the development, and after that you could apply the memory protection unit, and you will notice that the number of the safety violations happened while using the safety checker in an early stage, it will reduce dramatically.
Mm-hmm. Thank you. There's one participant wrote a lot of text, so I will try to summarize. So basically, this participant said that he's asking about challenge number 1 on the ACLD automotive project. So he's working for a team of developers who are doing some functional tests and unit tests, which are at C-source level. And it is software in the loop SIL testing. So, and the next step, they are compiling with the tasking compiler the same C code on the AURIX target. So they are running some integration tests on the hardware in the loop, so HIL, but they are in discussion now if they need to ensure the functional tests, which are originally ran on SIL, also must be rerun on the HIL to capture any tasking issues. So the question would be, basically, if they need to do a back-to-back comparison of outputs of SIL versus the HIL results of the same C source with the same input data, or could they simply ignore the back-to-back step and rely on the tasking qualification kit to guarantee the C code has the same behavior from SIL to HIL? So this was a lot of information.
Yes, I'm trying to digest the question.
Yes, but maybe we can also, I would propose if this participant can write us an email to our email. Maybe you go back one slide, Ahmed, because here's the email address, sales@tasking.com, and you can ask this question again. So we get also all your contacts details, and then I think maybe you can set up a meeting with Ahmed and to discuss this, because I think this is not as easy to be answered in a few minutes.
Yep, I totally agree.
So please just get in contact with us, and then we can set up a meeting together with you and we can clarify the issue. Okay, then there are some more questions. Can we get the example project used in the webinar?
Florian, do you know if we do?
I need to double check if we can provide this, because here we are also working together with partner Neutron Controls, which provided us the demo. We need to double check, but also here I would like you to get in touch with us on email conversation, and then we can discuss this topic. Then another question, is there support for auto-generated code, e.g. target link embedded coder?
Is there support for auto-generated code? What kind of support? The question for me, it's really not 100% clear. So what is the support that you are looking for? If you please maybe write this now, this would be this would be helpful.
Yes. So,
but as long as the code generation, for example, if you are using, for example, MATLAB, and you already generated ISO C code and then compile it with the tasking compiler, so this should be a really very valid case. But as I already mentioned, I need more input. What is basically the support needed in this case?
yes, also if you who asked this question, please contact us via our email address, then we can also get in touch with you after the webinar.
There is another question. Can you please send a link to the description of the measures ensured by the safety checker? So if you go to basically the tasking.com and you go to the under products, you could select as a safety checker, and you could download the document explaining the product itself and the different measures conducted by the safety checker.
Exactly, all the information on tasking.com. Then you go on the product menu and you find the product page for our safety check and all the relevant data sheets and product overviews. All right, I think there are no further questions so far. I would like to encourage you that you contact us if you are also interested in a free evaluation license of the Tasking Safety Checker. You can either request this via our tasking website and apply via the template, or you can send us directly an email to sales@tasking.com, and we would be happy to issue a free evaluation license of the Tasking Safety Checker or any other product which was presented during the last 3 webinars, as the Embedded Profiler Multi-Core Performance Tool or even the VX toolset. If you have additional questions, also feel free to contact us anytime, and our FAE team will be happy to set up meetings with you and support you with your questions. Then thank you very much for joining this webinar series. I wish you already a nice holiday season coming up for those of you who are celebrating Christmas, and get a nice holiday, and then hopefully we will see you next year. Again, thank you very much for joining.
Thank you, guys. Stay safe. Have a good day. Bye-bye.
Bye-bye.